Section 11.3, contingency tables, that S should be there, and test of independence. So previously we used the chi-square test for goodness of fit, and we're testing how well our observed data fits what we expect to happen. The chi-square statistic can also be used to test the independence of two variables, whether they're related somehow or if they're not. So let's say we wanted to see if there was a relationship between high school students who are on their way to college bound, and the number of extracurricular activities they are involved in. So what we're trying to see is, does the number of college or extracurricular activities that they are involved in some way predict or affect the students who are going to be college bound? We don't know, so we're going to test that. So we sampled 400 high school students, and we have to classify each student in two ways: whether or not they're going to college and how many extracurricular activities they are involved in. So the big difference here between a test of a goodness of fit is you're usually just going to have one variable with one attribute, like we had previously with the vitamins or with the rolling the die or the nurses and their hunch about the patients that come in. The only measurement we were taking, there was only one measurement, but here we have a student and we're classifying them two ways. So that's a big hint that you're going to do a test of independence. Now, if the proportion of college-bound students is relatively constant, despite the number of extracurricular activities, then we know the two variables are independent, meaning they don't affect one another. But if not, then somehow they are dependent. Well, to get started to test the independence of two variables, we have to set up our hypothesis. Our null hypothesis is always going to include something about the two variables being independent. So in this case, our null hypothesis is whether a student is college bound is independent of the number of extracurricular activities. So obviously the alternative hypothesis is that they are dependent. Now, whether a college student is college bound would be contingent upon the number of extracurricular activities they are involved in. That's what we're trying to show. So all of this information is displayed in a contingency table. So here we have our categories: either they're going to college or they're not. And then we've classified the number of extracurricular activities as either few, 0 to 1, some, 2 to 3, or many, 4 or more. And then we have the number of students that fell in each category. Now, the size of a contingency table is always stated as the number of rows go across, by the number of columns. Think of columns like columns that support a building contained in that contain observed data. So we don't want to count the totals columns or the titles or anything like that, only those that contain some actual data. So this contingency table is, we have 2 rows and 3 columns, and each box that does contain an observed data value is called a cell. So this contingency table has 6 cells. Now, our table contains observed frequencies, but just like we did with goodness of fit, we also need expected frequencies. In a contingency table, they're a little bit different to calculate than what we did for goodness of fit. So to find the expected frequency of each cell, we multiply the row total by the column total and divide all of that by the sample size. So to get started here in our contingency table, we need to figure out these totals first. So I'm going to add straight across for the number of students who are college bound, and I get a total of 236. And then same thing going across for those who are not going to college, and I get 164. And to double check, you want to make sure that those two numbers add up to 400, which they do. Now I have to do the columns. So for those who have a few extracurricular activities, I'll add 66 plus 37 for 103. And then for those who have some, that is 91. And for those who have many, that's 206. And I'm pretty sure that's going to add up to 400, but it wouldn't be a bad idea to double check. So now that we have the totals, I can find the expected value. So for here, for 66, the row total is 236 and the column total is 103. So I'll multiply those two together first. And then I'm going to divide by the overall total here, 400. Now usually the expected value should be in the ballpark of what the observed value is. And I get 60.77. I'm going to write that in parentheses to let myself know that that's an expected value. So I need to do that for each cell. So for 57, I would multiply 236 times 91 divided by 400, and that is 53.69. And now here's what I got for the remaining cells. So 121.54, I multiply 236 times 206 divided by 400. Here I get 42.23. For 34, I got 37.31. And for 93, I got 84.46. Okay? And those should still add up. There might be some rounding error, but they still should add up to the row totals and the column totals if you just want to double check that. Well, now that we have the expected frequency of each cell, we can start computing a chi-squared statistic. This is going to be exactly the same as what we did for goodness of fit. We're going to take each observed value, subtract off the expected value, square that, and divide by the expected. And again, I'm gonna let my calculator help me do the calculations a little bit faster. If you haven't already, make sure you take a look at the video that shows some screenshots from the calculator of doing that. But essentially what I'm doing here to calculate this chi-square test value is I would take, so for the first cell, I would take the observed 66 minus 60.77, that gets squared, and divide by the expected 60.77, and I would do that all the way down to the last one, 93 minus 84.46, that gets squared, divided by 84.46. So if you let your calculator help you out, you would type in all the expected or all the observed values in one column, all the expected values in another, making sure that the observed matched up with their respective expected value, and then add those all, or do the formula on them as I showed you in the video. O minus E squared divided by E. So for, depending on how you put it in your calculator, it'd be list 1 minus list 2 squared divided by list 2, and then add all those up, and I'm getting a value of 3.059. That's my test value. Now, similar also to what we did before with goodness of fit, we need a critical value. And again, we need degrees of freedom. But for a contingency table, it's a little bit different. It's not just the number of categories minus 1. Here it's going to be the row minus 1 times the number of columns minus 1. So for this example, we had 2 rows and we had 3 columns. So the degrees of freedom here will be 1 times 2, or 2. So for my chi-square statistic, and we will use, let's use alpha equal to 0.05. So looking up on our table with 2 degrees of freedom and 0.05, I get, so chi-squared with 0.05 for alpha and 2 degrees of freedom, I end up getting 5.991. Again, if you're a little more visual, we have this skewed distribution, and our critical value is here at 5.991. This is our rejection region. And our chi-square test statistic was 3.059, which probably falls about right there. So, for our conclusion, since we don't fall in the rejection region, we would fail to reject. H naught. And remember, you always want to state this in terms of the context of the problem. We would say something to the effect of, how did we state it before? We could say, whether a student is college bound, and the number of extracurricular activities are independent. So it sounds like it doesn't matter how many extracurricular activities a student is involved in, it doesn't tell us whether they're going to college or not.